Hello. Today we'll be discussing the topic parameter efficient transformers. So let's begin. Parameter efficient transformers are modifications of the standard transformer model designed to reduce the number of trainable parameters while maintaining the performance. These methods aim to make transformers more computationally efficient and easier to deploy in a resource constrained environment. In the first half of the presentation, we will be covering four research papers discussing their prerequisites, concepts, experiments, and results of each of them. In paper 1, Parameter Efficient Transfer Learning for NLP, we will be covering what is transfer learning, feature-based versus fine-tuning, adapter tuning, and architecture. In paper 2, LoRa, low rank adaptation of large language models, we will talk about fine tuning, LLMs, and parameter efficient approach, adapter modules and prefix tuning, intrinsic dimension and intrinsic rank, and LoRa. In paper 3, it's not just the size that matters. Small language models are also few shot learners. We'll discuss zero shot learning versus few shot learning, PET, pattern exploiting training, IPET, iterative variant of PET, and PET with multiple masks. For paper 4, making pre-trained language models better few-shot learners, topics are lm-bff, better few-shot fine-tuning of language models, prompt-based fine-tuning, automatic prompt generation, and fine-tuning with demonstrations. In paper 1, parameter efficient transfer learning for NLP, let's start. So what is transfer learning? It is machine learning method where a model developed for one task is reused as a starting point for a model on a different but related task. Basically, the concept is that there is no need to reinvent the wheel, but to use the wheel to make a car. This approach is more efficient and versatile as it can be used in many similar tasks and mostly results in higher performance. To understand the key difference between feature-based and fine-tuning, let's take an example. For someone like me who comes from India, where multiple languages are spoken, it is easier to learn a new language as many languages share similar features. And I can use the same understanding and concepts I have already learned and use them to my benefit to learn a new language. For a friend of mine who only speaks one language, it could be comparatively difficult to learn a completely new language as the similarities between both languages could be limited, leading to a requirement of more resources and time to get good at any new language. In feature-based, the original function phi_w is used as the base to train on new parameters v, making the new function as sky_v phi_wx. There is almost no change made to the original function and its parameters. In fine-tuning, the later half of the function is modified for the new parameters, where new parameters are introduced and old parameters are used to tune the model. A new concept of adapter tuning is introduced here, where the original function and its parameters are frozen during the time of training and new parameters are added in between the function in the form of adapter modules. It is like taking a time machine and adding only a few minutes of learning a new language every day in your entire lifetime without modifying the course of your life and the core understanding and learning of your original language. On the left is a basic transformer layer architecture that we have modified by adding adapter modules in between. On the right is a view of the adapter modules which we have used. Let us take a deeper look into each of them. In the transformer layer, the primary sublayer is the multi-headed attention layer, which processes the input data for the model. Then comes the feed-forward layer, where the data is processed using the attention mechanism. We will discuss the adapter layer in a bit. Then we see a plus sign, which is the skip connection. Here, the decision is made whether the output of the adapter or feed-forward layer is to be added to the original input layer or sublayer. This helps in preserving the information from earlier stages and making the decision whether this new process data is to be added to the network or not. Finally, we have the layer normalization, which normalizes the combined output provided by its previous sublayers. The adapter modules, which are added to the transformer layer, have a bottleneck architecture to it. This specific architecture helps us add only a few parameters ranging between 0.5 to 8%, making the total number of parameters as 2md plus d plus m. The number of new parameters that are being added can be controlled by increasing the size of this adapter module. Finally, there is a skip connection. Here, the impact of the newly added parameters are controlled by initializing it to a near zero at the start and slowly increasing it over the training. The goal of this paper is to help build compact and extensible systems that give good results on multiple similar downstream tasks where the new data that is coming into the system is unknown at the time of training. For this, the authors have used 26 different classification tasks to benchmark the results using BERT. Benchmark is an important benchmarking tool which is widely used to train and evaluate such natural language understanding systems. The key feature is that it is model agnostic and has a leaderboard and dashboard to benchmark and showcase the results. Squad, the Stanford question answering dataset, was also utilized in this paper. It comprises of 107,785 question answer pairs from Wikipedia articles in its 1.1 version. On the glue benchmarking tool, the BERT model with adapter modules matches the performance of fine tuning, and by only utilizing around 3% of the new parameters, the AutoML benchmark results are also good. BERT base with adapters utilizes only 1.14% new parameters and reaches a 73.3% accuracy, while BERT base fine tuning uses 100% new parameters and reaches 73.7% accuracy. The graph on the right also shows that the validation accuracy with adapter modules can be similar to fine tuning while utilizing 100 times less number of new parameters. Paper 2 is LoRa, low rank adaptation of large language models. This equation is used to predict the next word in a phrase. Here, YT is the next word and its probability is calculated based on the previous words Y0 to YT minus 1 and the parameters phi. In the fine-tuning, this equation is altered by replacing phi with new parameter weights y0 plus delta phi, where the dimension of delta phi and phi are not the same. In the parameter efficient approach, this is further altered by multiplying delta phi with theta, which is a which has like much smaller dimension than phi and phi naught. This is approximately 10,000 times smaller than phi naught. As we just learned about adapter modules, a question might arise that can we not use adapter modules in LLMs like GPT-3? And the answer is yes, we can, but adapter modules need to be processed sequentially, which leads to high inference latency and additional depth to our approach in large models like GPT-3. Let's address another question regarding prefix tuning here. In the later half of the video, we will look into prefix tuning, but I can just give a brief for now. In prefix tuning, we add instructions at the start of the training process and freeze the original parameters, but this will lead to inconsistent results and a difficulty to optimize the entire approach. Also, we will have to add a prompt before each input, which would limit the length of the tasks. We wish to process with the model. Hence, these two approaches are possible, but come with their own flaws. Let's understand two key concepts we would require in this approach. Number one, intrinsic dimension, which refers to the minimum number of parameters needed to get the performance similar to the full model. It is basically the simplest version of the model that does similar level of work. Second concept is intrinsic rank, which is the complexity of freedom in a particular component of the neural network. Basically, it indicates the minimum number of dimensions needed to represent the important information in that component of the neural network. These concepts are usually paired together where we find the intrinsic dimension for the whole architecture and the intrinsic rank at each step to optimize our approach to use the least number of features. This is the main concept that is being utilized in LoRa. Here, the pre-trained weights are frozen during the time of the training, and the new parameters that are being added to the model are added in a matrix multiplication format represented by A cross B matrices here. The intrinsic rank, which we just discussed, R is much lower than both D and K, which are original dimension length that was being utilized by the neural network. Here, B is initialized as 0 and A is initialized in a random Gaussian manner. And this is done so as to feed the model with very less number of new parameters at the start and is scaled eventually to reduce the need to retune hyperparameters. Finally, the forward pass using LoRa, which is W naught X plus BAX, has a lower rank and uses much less number of parameters than usual. The experiments in this paper were conducted using Roberta, DBERTA, GPT-2, and GPT-3 was finally used for comparison. This was done over the glue benchmarking tool and various datasets like WikiSQL, SamSum, A2E NLG, Dart, and Web Energy. These are some commonly used datasets and benchmarking tools to test natural language understanding systems. On the glue benchmark, we can see the approach using Roberta base with LoRa only utilizes 0.3 million new parameters to result in an 87.2% accuracy using the least number of parameters, other than the approach with BitFit, which results in a much lower accuracy of 85.2%. And in the E2E NLG challenge with GPT-2, the approach with GPT-2 medium with LoRa uses only 0.35 million new parameters to give the highest accuracy in all cases when compared to fine-tuning, which used 354.92 million new parameters to give a lower accuracy. A similar trend can be seen in the GPT-2 large trainable parameters and accuracy with LoRa outperforming other approaches in most cases. When LoRa is utilized with GPT-3, we can see it only uses 37.7 million and 4.7 million new parameters to reach a slightly higher accuracy when compared to fine-tuning with 175 billion new parameters. These trends are mapped out on the graphs on the right as well, where LoRa outperforms all the other approaches in terms of accuracy. Paper three is not just size that matters. Small language models are also few-shot learners. Let's firstly understand zero-shot learning. This is the approach when a model is trained for a variety of tasks and is later applied to a new task and given no new examples to learn from. In this, the model relies on its general understanding and knowledge gained during the original training to make predictions about the new task. Few-shot learning is similar to zero-shot learning, but a few examples related to the new task are used to fine-tune this model. This usually results in better accuracy than zero-shot learning due to the new examples. For let's consider a model when trained on English language dataset is applied for sentiment analysis on French language data directly, then it is zero-shot learning. But when the same model is fine-tuned on a few examples which contain documents with French language in it, then it is few-shot learning. PET or pattern exploiting training. Here an input x1, x2 is converted to a closed question px, and the probability qpy by x is derived for the possible choices of outputs that fit the input to complete the closed question using a Mars language model or MLM, as given in the example. Here, x1 is oil prices fall back and x2 is oil prices rise. A yes or no needs to fit in the blank space between x1 and x2 to connect these inputs to complete the closed question. This is done using a pair of pattern verbalizer pairs or PVPs, which help map inputs to outputs. Here, P maps inputs to close question containing single mask, and V is used to map each output to a token representing its task-specific meaning in the pattern. QPY by X is calculating using the raw position of VY, that are the possible outputs to complete the close question, at the masked position in PX. As we are using few shot learning, that is a less number of examples to fine tune the model, we need multiple PVPs, and a combination of these is used to determine the output. These PVPs are used to assign final probabilities to the unlabeled examples, resulting in a probability distribution of each unlabeled input to a possible output. IPET, or iterative variant of PET, is similar to PET, where the flow comprises of three main steps. Number one, initial training, where an ensemble of MLMs are trained using PET, as we just discussed. Number two, creating new training sets, where each model in this ensemble uses a random subset of trained models to label a set of unlabeled examples. Number three, retraining models, where each model is retrained on its newly created training set, and step two and three are repeated multiple times by changing the size of the training set by adding more and more examples to it. PET with multiple masks. This is similar to PET with single mask, just that the prediction word would be longer and needs to be broken down into multiple masks, just like the one in the example. Here the input X is awful pizza, is followed by it was, and multiple masks to form a close question. Instead of mapping the input to outputs, here they are mapped back to the possible outputs, and then the process is repeated to find the best set that fits the complete close question. If we take the example of sentiment classification of restaurant reviews, we can broadly divide the reviews as positive, that is +1, and negative, that is -1. We calculate the probability of each word that can fit each part of the mask token for each set, and finally recalculate the best token that fits the close question. PET is based on Albert, and the authors have used an advanced version of glue benchmark known as superglue. This benchmarking tool contains more challenging tasks like bool queue, COPA, etc. The authors have developed a variation of superglue known as FuGlue to evaluate language models like PET and GPT-3. FuGlue was developed by randomly selecting 32 examples from each superglue task to ensure consistent and controlled selection of the data. They also created sets of unlabeled examples up to 20,000 for each task by removing labels from the original training sets to evaluate the model's unsupervised and semi-supervised learning capabilities. The results showcase that PET and IPET model outperforms on the 32 randomly selected examples after training on FuGlue with Albert XX large V2 than most of the GPT-3 models on SuperGlue. These are some extended examples where PET outperforms or closely matches the accuracy of most in-use models today. Paper 4 is making pre-trained language models better few-shot learners. This paper builds on the previous paper we discussed and introduces lm-bff, a better few-shot fine-tuning of language models approach. It's a three-step process which involves taking the new task and automatically converting it into a prompt. An example from each class of the training data is added to the prompt, which is then fed to the LLM. We can see this as a task that is an input which can be converted to a prompt, which fits the basic format for the LLM. This prompt also includes examples from every class. We can see that as one example from each positive and negative class from reviews about the restaurant. The first step is prompt-based fine-tuning. The input task is converted to fit the right format by the LLM. For example, with the CLS token at the start and SEP token in between the different inputs. This input also contains the masked word, which is the mask token. This prompt is an extended answer for the possible direct input, like no reason to watch, where the prompt would be it was great or it was terrible. These tasks can be classification or regression tasks. For classification, a single probability is calculated for the masked word to help classify task label space to individual words in the vocabulary based on the prompt. For regression, the final probability is the sum of all the probabilities of possible sets, example positive and negatives. The second step of automatic prompt generation is divided into two parts: automatic selection of label words and automatic generation of templates. In the automatic selection of label words, a set of top K vocabulary words is constructed for each class. In automatic generation of templates, the authors have used a large pre-trained text-to-text transformer T5 to input sentences from the training set and fill in template tokens like X and Y to create an initial template for the prompt. All these templates are built using a label mapping scheme. These help find the final output template that best fits. This is done by testing them on datasets DDEF. In the final step, fine-tuning of the LLM takes place by taking the prompt generated before and extending it with examples of each class. This can be seen in the example where no reason to watch is the input and a template it was mask was added to it at the end of it, and a positive demonstration of a fun ride it was great, and a negative demonstration of the drama discloses nothing it was terrible were also added to the prompt. This is then repeated to fine tune the LLM over the entire dataset to help with the few shot learning. For the evaluation of this, the authors use Roberta Large over 8 single sentence and 7 sentence pair English tasks, including 8 tasks from the GLUE benchmark, Natural Language Inference (SNLI), and 6 other popular sentence classification tasks. And the average performance is measured across 5 different randomly sampled D-train and D-dev splits. In the tables, we can see the templates that were utilized for this. The results are great, as we can see that this method outperforms prompt-based zero-shot in-context learning with fine-tuning of GPT-3 in most of the cases. These results also show both automatic prompt generation and manual prompt generation outperform other models. These results show a fair comparison of this three-step approach with PET as discussed earlier, and the graph shows the accuracy versus instances of standard fine-tuning versus lm-bff, where the latter outperforms the former. I would highly encourage everyone to check out the code of all 4 papers on GitHub, as they are well documented and easy to use.
And so now I'll be covering the second half of this presentation where I cover additional parameter-efficient fine-tuning methods, that is prefix tuning, prompt tuning, and IA cubed, and then I'll look at understanding PEFT more broadly, and that's through a unified view of PEFT and comparing PEFT with full model fine-tuning. First, I'll look at this paper that introduces prompt tuning. And before I cover prompt tuning, some background in prefix tuning is necessary, where in prefix tuning, we learn a small fixed set of additional parameters, that is, the prefixes. So to do prefix tuning, we prepend some number of tunable prefix vectors, or L tunable prefix vectors, to the keys and values of the multi-head attention at every layer. More formally, mathematically, given a query vector X and a sequence of M vectors C over which we would like to perform attention, normally multi-head attention takes this form, where we have the query's keys and values, where we take the relevant vector and we map it to query's keys and values through these weight matrices. But now multi-head attention with prefixes looks like this, where now the keys is actually the concatenation of the keys as they were before, but also now these prefixed keys. And same with the values. So the concatenation of the values as they were before, but now with the prefix values. So two sets of L prefix vectors, P sub k and P sub v, are concatenated with the original keys and values at every attention head and every layer. And now we just have to learn P sub k, and P sub v instead of all of the model parameters. Now I get into prompt tuning, which is a descendant of prefix tuning. So where in prefix tuning we were prefixing activations appended to the keys and values in each layer and each attention head, in prompt tuning we prefix k tokens to the input text, and then we just learn the token embeddings. I'm assuming we're all familiar with tokenization, but here is an example where we have this as an input text. It gets broken down into these tokens, start of sequence token CLS, and then basically the words become tokens, although there's also subword tokenization, but that isn't shown here. But basically these tokens then get mapped to token IDs, which then get mapped to embeddings through an embedding layer. But in the case of the prefixed tokens, they don't really correspond to tokens in the vocabulary, they just have some associated embeddings that we then learn in prompt tuning. How are these methods evaluated? Well, they're evaluated using the T5 lm-adapt model of all sizes. So there's sort of a scale shown there, right? Where we have the small models that have about 60 million parameters, and the XXL model in the higher range has 11 billion parameters. And the models are evaluated using the superglue benchmark, which is a collection of 8 challenging English language understanding tasks. For example, one of which is BoolQ, which is a question answering data set involving, I believe, Boolean answers. So the first question that they try to answer in this paper is, how should the prompt be initialized? And 3 different alternatives are considered. One is that the prompt is initialized randomly, so each number in the embedding is just a random number, or perhaps prompts can be randomly sampled from the model vocabulary or from the 5,000 most common tokens in the vocabulary. So we choose random tokens, maybe dog, sky, and purple, which all form their own tokens. And we just take the embeddings of those random tokens, initialize using those, and then we learn from there. Alternatively, embeddings can also be those that enumerate output classes. So if I'm trying to learn a news classification task where I have a passage and I'm trying to classify it as news related to the world, news related to sports or business news, then I can just take those output classes, find the relevant token embeddings, and initialize using those, and then we learn our embeddings from there. Right, and just as a reminder, prompts are represented as a parameter P sub E that are matrices of size P times E, where E is the dimension of the embedding space and P is the length of the prompt. Right, and what they find is that while they say that class label initialization performs best, and they also say that at smaller model sizes, there are large gaps between the different initializations, but once the model is scaled up to the XXL size, these differences disappear. But I wanted to ask, does the chart suggest the same? And so here we have a chart where the x-axis is model parameters, and the y-axis is the average superglue score. And then we have the 3 methods: random, uniform, sampled vocabulary, and class label. And first they say class label initialization performs best, but I think the chart suggests that basically class label initialization and sampled vocabulary perform very similarly, and they walk hand in hand. And then for random uniform, they say that smaller model sizes, there's larger gaps, but once we grow the model, the gaps shorten. And certainly at the largest model, all 3 methods perform very similarly, but also in the smallest model, they perform similarly. I think the random uniform just has more noise and is a method with more variance. Second question they attempt to answer is, how long should prompts be? And they find that across all models, increasing beyond 20 tokens only yields marginal gains. And in fact, with the XXL model, it still gives strong results with a single token prompt, suggesting that for larger models, prompts don't need to be as large and not as many parameters need to be learned, right? Actually, what's interesting is that in the case of the T5 XXL model, a single token embedding has dimension 1024. So we're only learning 1024 parameters, and that seems to work well. So that is quite interesting. And now comparing to other methods, Interestingly, the paper doesn't make effectiveness comparisons with other PEF methods. Only comparisons to full model fine-tuning are made for effectiveness. They do compare parameter usage with other methods, right? And they argue that prompt tuning is the most parameter efficient method because it learns very few parameters across the range of model sizes. But it is interesting that they did not make comparisons with other PEF methods for effectiveness, right? On one hand, making these comparisons would have required them to reproduce these other methods, which would have been more work. But on the other hand, I argue that their work on a PEF method is incomplete without effectiveness comparisons to other PEF methods. They do make comparisons again to full model fine-tuning, and so we show this, right, where prompt tuning becomes more effective with scale, they show. Prompt tuning matches even the stronger multitask model tuning baseline, and that is a baseline where a single model is tuned on all the superglue tasks at the same time. And so that's the strongest baseline and achieves the strongest results. But for a sufficiently large enough T5 model, prompt tuning does just as well as full model fine-tuning, or multitask full model fine-tuning. The fourth line there is prompt design, the blue line, and that measures the performance of GPT-3 in a few shot in context learning example. So their method where they train actually does better than GPT-3, just using the T5 model. And so the final part of this paper that I'll look at is resilience to domain shift. And domain shift is a change in data characteristics across contexts. Perhaps you train in one context and then you try to evaluate the model in another context. In this example, the model is trained on the Stanford question answering dataset, and it's evaluated on these other datasets, so out of distribution, right? So the Stanford question answering dataset has passages from Wikipedia, and then we try to answer questions given those passages. But the textbook QA dataset actually has passages from, I think, a middle school level textbook. The questions are also the middle school level knowledge questions. And BioAsk, I believe, is a biomedical question answering dataset where the domain is biomedical papers, I believe. Right, and so we see that the prompt tuning method actually does very well in these settings compared to full model fine tuning. But again, in this table, there are methods where full model fine tuning does better. But anyway, the authors argue that by freezing the core language model parameters, prompt tuning prevents the model from modifying its general understanding of language, and this reduces the model's ability to overfit to a dataset, which would be bad. That's not something that we want. So they argue that prompt tuning may improve robustness to domain shifts. But I present this table as it is. And so you might disagree with that. If the results aren't, a clear prompt tuning looks better. I'll now move on to the second paper entitled Few Shot Parameter Efficient Fine-Tuning is Better and Cheaper Than In-Context Learning, where they introduce a new PEF method, IA cubed, that comes from this name. And the idea of the method is that they learn L sub k, L sub v, and L sub ff, which are vectors, with the task of rescaling via element-wise multiplication the keys and the values in attention, and the inner activations in feed-forward neural networks, or in the network. Right. So here we have the attention mechanism, and the values are rescaled using LV, the keys are rescaled using LK, and then in the feed-forward network, after the dense layer and the nonlinearity, there's L sub ff, which rescales whatever is output from there. That's going into the next dense layer. So again, this paper introduces this method, and it argues that PEF is better than ICL in few-shot settings. And just to remind you, few-shot learning is learning from only a few examples, and ICL is in-context learning, where we induce a model to perform a downstream task by inputting prompted examples. And so here's an example of both few-shot and ICL. So it's a 4-shot input or context that is, please unscramble the letters into a word. So we're asking the model to unscramble these letters and write the word out. And so here are 4 examples. For example, ASINOC gets rescrambled to casino. Right? And so we wanted to unscramble that last example, ASTEDRO, and it would hopefully rescramble that to roasted. Now, what's wrong with in-context learning? Well, the advantage, the authors say, is that ICL, they recognize, does enable single models to perform many tasks without fine-tuning. But the disadvantage is that making predictions is expensive because the model needs to process all the in-context examples every single time a prediction is made. So instead of in-context learning, PEFT is a promising alternative. So how they evaluate their methods is they use the T0 model, which is created by fine-tuning the T5 model on a mixture of datasets to enable zero-shot generalization. For each dataset that they test, the number of few-shot examples used varies from 20 to 70, and that's not arbitrary. They do that to match the same number as the evaluation from the paper, language models or few-shot learners. And that's a paper that looks at few-shot learning with the GPT-3 model, and that's a paper by OpenAI. And so the data sets they consider stretch, these 4 different areas: sentence completion, natural language inference, co-reference resolution, and word sense disambiguation. Very quickly, sentence completion is, given one sentence, you just complete it. Natural language inference is given some premise, we classify whether or not another premise is logically entailed by that first sentence or by that first premise. So if we say, she was playing golf with Ron when her phone rang and it was Liz, her mother's friend. If we say that Liz called Taylor, that is logically entailed. If we say Ron called Taylor, that's a contradiction. That doesn't make sense. And if we say a doctor called Taylor, perhaps Liz is a doctor, so that's unknown logically. Co-reference resolution is recognizing whether or not an entity is referring to the same thing as another entity in some text. And word sense disambiguation is figuring out in what sense do we mean of the word. If we say something like, please open the window to let some fresh air in, are we referring to, the kind of window that we look out of to see outside, or are we talking about the operating system? And so here are the results. They compare IA cubed both with other PEF methods, and they compare IA cubed in the T-few model with ICL. And so it's actually pretty confusing. So there are a number of things I need to explain. First of all, the comparison with PEF methods is made with the 3 billion parameter version of the model, and the comparisons with ICL is made with the 11 billion parameter version of the model. They say it's just quicker to evaluate with 3 billion parameter models because it's just smaller and easier to work with. So starting with the left figure, we see that IA cubed actually does very well. It beats full model fine-tuning, which is marked by the dashed line, and it beats the other methods. Some of these which we have covered, like adapters, prompt tuning, prefix tuning, and LoRa. And it does so with not a large amount of parameters updated, a relatively modest amount. So now comparing to ICL, these baselines are not intuitive, so let's explain. T-few is just taking a T0, fine-tuning it with IA cubed, and then evaluating that, and that performs the best in terms of accuracy. And x-axis is number of flops per example, so the amount of floating point operations needed to make a prediction, right? So T0 evaluates the T0 11 billion parameter model in a zero-shot setting, so without any training or without even in-context learning. And that actually does fairly well and does better than GPT-3 in the in-context learning setting. So that's a relevant baseline to include. The T5 plus LM actually evaluates the T5 LM adapt 11 billion parameter model with ensemble ICL. So it's using ICL. And because the context window of the T5 is so small, each example is basically its own context. And then the predictions are averaged. So if I have 4 examples, there are 4 predictions made using the T5 model, and then those predictions are averaged. And they don't do ICL with the T0 model because they showed that actually the results were worse than not using ICL. So the baseline model for ICL for the T5 model is this, which actually performs the worst of all the methods in that figure. And then there's the GPT-3, which is the strong ICL baseline, which performs relatively well, but it takes a lot of floating point operations to compute, and in fact, it still doesn't do as well as T-few. Right? So now making arguments about efficiency, the T-few method shines in terms of inference floating point operations. It is very cheap to make a prediction compared to the other methods, especially the ICL methods, right? That being said, it is a model that is trained unlike the other methods, and so there is a cost to that. So the flops again are the floating point operations to make a prediction for a single example. And so again, T-few method performs the best. It has low inference floating point operations, but it does take some cost to train. And the disk space is not too interesting, but basically the parameters of the model need to be stored. And so the extra cost of storing those models is, a disk space usage of 4 megabytes, which is basically nothing because these models and their weights already take, gigabytes to store. The 11 billion parameter model, I think, is probably like 30 gigabytes to store. And the GPT-3 models at 170 billion parameters will be a lot to store. But that 4 megabytes is the cost of storing the additional parameters, and the 16 kilobytes is the cost of storing the input prompt for each task. 16 kilobytes is basically nothing, right? Now, that's some criticism of this work that I wanted to share. One is that the experiments were on classification tasks only. Optimally, I'd like to see experiments done on other tasks, for example, generative question answering. Another criticism is that the valuation was only done using the T0 model. Optimally, as a parameter-efficient fine-tuning method, it should be evaluated in other models as well. The T0 model is an encoder-decoder model. Maybe some experiments should be done with encoder-only models like the BERT family of models, or decoder-only models like a lot of the open LLMs that we're seeing today, like Llama or Mistral. Final criticism is that the valuation of the PEFT method is only done in the few-shot setting, and that is the point of the paper, I recognize that. But I would have liked to see the evaluation of this method in a more high-resource setting where a lot of training data is made available. And now that brings me to this paper that is towards a unified view of parameter-efficient transfer learning, which relates prefix tuning to adapters and then tries to draw new insights from that relation. Mainly, they try to answer, so as I just mentioned, can adapters, LoRa, and prefix tuning be related to one another? And in fact, they can, and a unified understanding of these allow for the creation of even better parameter-efficient fine-tuning methods. We call adapters. We've already covered this, but basically the adapter approach inserts small modules between transformer layers. And so there's a down projection matrix and an up projection matrix and a nonlinear activation function. And I'll go very quickly over this, but basically we can derive a new functional form of what the adapter is doing, where the new hidden states equals the old hidden states plus the output of the adapter, which is the activation, the old hidden state times the down projection, and then all of that matrix multiply with the up projection. So let's remember this for later. Now let's try to derive a similar functional form for prefix tuning. So to do prefix tuning, again, we talked about this, but to recall, two sets of our prefix vectors are concatenated with the original keys and values at every attention head in every layer, and then given a query vector x and a sequence of m vector c over which we would like to perform attention, that prefix tuning takes them in this form, right? We have the queries, the keys, which is a concatenation of pk, and the keys as they would have been otherwise, and the values, which is the concatenation of PV and the values as they would have been otherwise without prefix tuning. Now, this statement can actually be rewritten as this. And I've skipped a few steps, but basically it takes on this form, where lambda x is a scalar that represents the sum of normalized attention weights on the prefixes, and in this formula, I and j index values in the vector. Basically, lambda x is a scalar, and we've rewritten prefix tuning as this form, where as attention was before just on this form, right, with the queries, keys, and values, with prefix tuning, we've separated it out into as it is normally attention, but also the added modification with prefix tuning. So alternative view of the prefix tuning in the functional form we've been considering is of this form, right? H takes on 1 minus lambda x of h as it was before, plus lambda x times the modification to h, where again delta h is a modification to the original head attention output h through linear interpolation. And it's linear interpolation because of these scalars, 1 minus lambda x and lambda x. So now relating prefix tuning and adapters, again, we have this functional form for prefix tuning, and we have this functional form for adapters. Now, if we define W sub 1 as this, and W sub 2 as this, and F as the softmax function, well, then we can rewrite what we have, the functional form of prefix tuning, to this, which looks a lot like adapters, except that prefix tuning is doing weighted addition because of those lambdas. Now we have these very similar functional forms, but there are some key differences. One is that prefix tuning uses x to compute the change to h, while adapters use h to compute the change to h. And so there's a difference there in parallel versus sequential computation. And that might be easier to understand if you look at this graphic, where in adapters, we first pass the inputs x through the PLN module to get h, and then that h is taken into the second adapters branch to compute the new h, the new hidden state. Whereas in prefix tuning, we don't pass x through the PLM module to go into the second branch. It actually is passed right into the second branch. So we have basically h as it would have been without prefix tuning and h with prefix tuning, and then we can add these together, right? Another difference, though, is that adapters are more flexible with respect to where they're inserted. Adapters can modify both attention, but also the feed-forward net outputs, while prefix tuning only modifies the attention output of each head. And so you might see that in this transformer block, where adapters can be inserted here, right after the attention module, or adapters can be inserted here, right after the feed-forward network. Whereas with prefix tuning, we see that the P sub k and the P sub v are only basically changing things within the attention module. But now to summarize the differences between prefix tuning, adapters, and LoRa, which is also similar and relevant, first let's look at the insertion forms. So as we just mentioned, adapters are sequential, but prefix tuning and even LoRa is parallel. And so you can see that in this graphic for LoRa. As for what representations they modify, as we just mentioned, adapters can modify both feed-forward network part and the attention, whereas prefix tuning can only modify the head attention, and LoRa can only modify the keys and the values in attention. Right. So LoRa, again, in the transformer block, LoRa modifies here the weights matrix for queries and the weights matrix for keys. And then we have these composition functions, which we've been looking at. And there's a new one for LoRa, where basically the composition function for LoRa looks a lot like adapters, but there's the addition of this S hyperparameter, basically that scales the change to h. And we have the functional forms for delta h here. Now, how can these methods be used to formulate new PEF methods? Well, there are a bunch of differences, right, between these methods. So we can test and compare which variant of these differences performs better. So we can compare parallel versus sequential insertion, modifying attention representations versus modifying the feed-forward network representations, and scaling the composition function or leaving it unscaled. And so in evaluation, these are the data sets they use. The XSUM dataset, which is a news article summarization dataset, English to Romanian translation, MNLI, which is a natural language inference dataset, and SST2, which is a sentiment classification dataset. And they evaluate on these datasets using these models. The BART large model, which is an encoder-decoder generative model for the summarization and translation tasks, and Roberta base, which is just an encoder model for MNLI and SST2 tasks, which can be shown as just classification tasks. So now the first question is sequential or parallel. What is better? Right? Well, prefix tuning, which uses parallel insertion, outperforms sequential attention sequential adapters. So we see that in this table, where the parallel adapters basically do better than the sequential ones. And prefix tuning, which is a parallel method, does better than the sequential adapters as well. One thing to note is that the number of parameters changed is kept comparable using these hyperparameters L and R, where R is the bottleneck dimension in the case of LoRa and adapters, and L is the length of the prefix in the case of prefix tuning. Right. So a parallel adapter from this work is able to beat sequential adapters in all cases. And the parallel adapter is something that they introduce here. Okay, and the second question then is, do we modify attention or the feed-forward networks? Right, so some observations is that any method with feed-forward network modification outperforms all the methods with attention modification in all cases. And so here's this graphic where we have in red the methods that modify the feed-forward network, and in blue the methods that modify attention. And clearly the red methods do better across the number of parameters fine-tuned. However, modifying head attention shows the best results when the parameter budget is very small. And so that's shown in this table here, where when the number of parameters changed is kept very small, actually the method that modifies the attention performs the best. And that's a parallel adapter that modifies attention, but also prefix tuning, which also only modifies attention, does better than these other methods. A third question to answer, which we've covered, is should the composition function be scaled or left unscaled? And they find that the scaling composition function is better than the vanilla additive one. You just have to find the right S value. And so in the table here, we have LoRa with S equals 4 versus S equals 1, where 1 is basically a default, and S equals 4 does better. And then you have parallel adapters with S equals 4 doing the best, and a trainable S doing not as good as S equals 4, but still doing better than parallel adapters in the default, where S equals 1. Right, so a learned scaler does not give much better results than manually tuning the scaler, which is interesting. But here's where sort of the unified view comes, where the best design elements can be combined to create an even better parameter efficient fine-tuning method. Right? So they found that the scaled parallel adapter is the best variant to modify the feed-forward network. They also found that feed-forward networks can better utilize modifications at larger parameter counts. However, when the parameter budget is small, so only when we want to modify a small number of parameters, that actually modifying head attentions with prefix tuning can achieve strong performance. Right, so this paper presents this method, the mix and match adapter, that combining all of these findings actually attains strong results. And we see that in this table here, where it is compared against both full model fine-tuning, a lot of the methods that we've talked about, prompt tuning, prefix tuning, LoRa, parallel adapter, which they introduced in this work as well. And basically the mix and match adapter, which combines a lot of the findings, performs the best. Although compared to full model fine-tuning, it's a hit or miss. So sometimes it'll do better, sometimes it'll do worse. And so that's interesting, right? And so concluding that last paper, moving on into trying to compare parameter efficient fine-tuning and full model fine-tuning, up to this point, it looks like full model fine-tuning can do better sometimes. Parameter efficient fine-tuning can do better sometimes with its advantages. So what do you pick? Right? And so they provide a number of relevant observations. They find that parameter efficient fine-tuning methods perform the best in low to medium resource scenarios, whereas full model fine-tuning does better in high resource scenarios. Now, what does that mean? Because it is arbitrary. So basically to them, low resources at most 100 data points, medium resources at most 1,000 data points, so ranging from 100 to 1,000, and high resource is at most 10,000. Realistically, anything more than 1,000. But in their testing, it's 1,000 to 10,000. right? So PEF methods do better in low resource, full model fine-tuning does better in high resource. Although looking at the table, in low resource, sure, all the parameter efficient fine-tuning methods are leading with medium resource. Full model fine-tuning actually leads in this data set, but in other data sets, it's PEF methods that are winning. And then in high resource scenarios, full model fine-tuning does better in 2 of the data sets, but it's still parameter efficient fine-tuning methods that do better in the other 2. Now, they also show that parameter efficient fine-tuning methods are slower to converge in low resource scenarios, but faster to converge in high resource scenarios. So basically, their general advice is that if you have a lot of training data, the parameter efficient fine-tuning method will be quicker, but it won't perform as well. And if you don't have a lot of training data, the parameter efficient fine-tuning method will do better, but it will be slower to train, which are both considerations if you're training models. And so in application, Hugging Face PEF supports many of the fine-tuning methods we discussed on modern models out of the box. So they've already been shown to work with these methods, and really with some manual modification configuration, these models or these methods can be used with any models, right? Or most models. And so here's this table where they've shown sort of what they've been able to do. And so with Mistral models or Llama models, these methods have been shown to work, but with configuration, most models will work with the parameter efficient fine-tuning method you choose. And it's already been implemented. Thank you. That concludes my presentation.